Welcome back. So this video will be about one-dimension friction. I'll try to make it as brief as I can. I'll do a couple example problems, and then you guys can get to your work. So you've been working with friction before. You know it's an opposing force to motion. So friction comes from two surfaces in contact, and it has its own equation. So the force of friction is equal to this coefficient mu multiplied by the normal force. More often than not, if there's no other vertical forces, the normal force could just be thought of as its weight. But that, if you just always do that, that will give you some problems later on. But for most purposes, you can just consider that the weight. So the coefficient of friction here, mu, is a dimensionless coefficient. There's no units involved, and you'll notice there's no vector symbols on these forces as well, because more often than not, if we're talking about moving across the ground here, friction is usually in the x direction, and the normal, if you recall, is the perpendicular force to a surface. So they're in an x and y direction. So we look at these more as a magnitude. So there is no vector notation in your friction. So plus the units will cancel out when you actually divide by the normal force to solve for mu. So you don't typically have to worry about the units as far as figuring out your coefficient of friction. So where it actually comes from is when you have two surfaces that are rubbing against each other. So if we take this little block, this blue block here on a surface, if you look at it and magnify it, you will see that it's pretty hard to actually have a real smooth surface. Most surfaces under a microscope are pretty rough. Yes, you can manufacture some that are perfectly smooth, but that gets pretty pricey when most of the time your fingers wouldn't even notice all these little ridges. But as you have two surfaces rubbing against each other, those little ridges catch, and it actually creates a little bit of resistance when you're trying to push or pull something. So that's where friction comes in. Now there's two types of friction. There's your static friction. So this is the friction you have to overcome just to start something to move. So static friction is a little bit stronger, right? It's at an at-rest state. So again, if you think of Newton's laws of motion, his first law of motion was the law of inertia. Objects at rest want to stay at rest until an opposing force acts on it, or an applied forces act on it, rather. And so in order to get something to move, you actually have to overcome this static friction. So the graph here to the right more or less shows you that an object will remain at rest. So again, this is not a zero acceleration. It could be moving type of thing. It is at rest. So you have to have a much larger force just to get something to move than you do to keep it moving. So that's when it starts to move. You can call it your sliding friction if you want. But the amount of friction necessary just to get all these ridges out of their grooves. So if you want to think of it like that, all these ridges out of their grooves, once they're out of their grooves, it's a lot easier to get things to move, to keep things moving rather. So your static friction is quite a bit larger. So in order to initiate motion, your applied force has to be greater than or equal to your force of static friction. So if it's equal to your static friction, that's typically the threshold of when we say, okay, it can now begin to move. So that's often what we do is like, oh, all right, how much force must be applied to get this thing to move? So you just more or less set these two guys equal to each other. And then at that point you go, okay, so if your force of static friction is 5 newtons, then your applied force has to be 5 newtons plus 0.00000000 something slightly larger, and it will start to move. So we more or less just make these two guys equal and say, okay, it'll begin to move once your applied force is equal to your force of static friction. So therefore, the more generic global equation is, in order to initiate movement, your applied force has to be greater than or equal to your force of static friction. And then it'll definitely start to move. Your kinetic friction, or your sliding friction, which is also one of the names, is the friction that you have when the body's in motion. So you might have experienced this before when you're pushing something. Once you get it to move, it's actually not that bad for a lot of things. So the idea there is that just once an object's moving, you have less friction to overcome, because if you remember that those ridges there, they're just bumping over top of the tops of the ridges when you have two objects in contact. So in order to keep something to move, Your applied force at this point just has to be greater than or equal to your force of kinetic friction. So if you're on the highway, for instance, and you have your car on cruise control, your forward acting force of the car, like the engine causing the tires to roll, just has to balance out the road friction, right? And you'll stay at a constant speed moving forward. And air resistance as well, if I group that in there. So, but let's ignore air resistance for this purpose. All right, so these forces would just be equal, and you'd have no acceleration, and you'd keep on moving. If you take your foot off the gas pedal, well, then all you'd have is your friction. And at that point, you would start to slow down until you come to a stop. So just to keep things moving, your applied force has to be at least equal to your force of kinetic friction. So the friction values, so the coefficient of kinetic and static friction values really depends on the two surfaces that are in contact. There's many charts that kind of give you a rough idea, and if you notice, a lot of these numbers are just a one significant figure, because it's really hard to actually pinpoint an exact number, because it's hard to have uniform smoothness or roughness of any two surfaces. All right, so I can say that, for instance, dry oak on dry oak, sure enough, the force of static friction is 0.5. But if it's really rough oak, so wood in this case, then it'd probably be a little bit more. If it's perfectly smooth and somebody had really fine sandpaper, then maybe it's probably around 0.5 for sure. But there is a range. So charts are only so good. Most of the time you just end up calculating it yourself, but it does give you an idea of how good two surfaces will be in contact as far as their friction is concerned. So if you pick on just rubber, now again, there's many different types of rubber, so let's just a generic rubber. If your vehicle is at rest, so rubber tire on dry asphalt, so on the road, your coefficient of static friction is approximately 1.2. So if you consider the equation for your friction, so that would mean that you would have to take your weight and multiply it by 1.2, and that would be the friction keeping the car at rest. Right, so it'd be quite a bit more. Once it's moving, however, that's a different story altogether. Your coefficient of kinetic friction is a little bit lower. So you'll kind of notice as you go across each of them, it's a little bit lower, sometimes significant, sometimes just only a tad bit. And so the actual coefficients will depend on how smooth or rough an object is, whether it's wet or dry. Different temperatures can cause these values to change a little bit, even if, whether or not there's any kind of a static charge on them. So it really does depend on, especially if you put any kind of a grease or a lubricant on them, and then everything just changes. So just so that you think about that. I'll do two examples here. So suppose you're driving the speed limit, so that's roughly 14 meters per second across town here in your truck. And so I can't remember if this is a Ford F-150 or a Chevy 1500, it doesn't matter. Half-ton truck, approximately 2,300 kilograms. So you're driving along and a kid jumps out on the road. You slam on your brakes and your tires lock up such that the rubber is skidding on the asphalt. So given the coefficient of kinetic friction between rubber and asphalt is 0.8, so according to that chart, what is the maximum deceleration of the truck? So what rate will the truck slow down? And B, what distance does the truck need to come to a stop? So this is just a basic physics problem. And because forces are involved, we start off with drawing a free body diagram to highlight all the forces that are acting on this truck. So I start off with the vertical forces mostly because a lot of the times they just cancel out. And so it just keeps life a little bit easier just to point them out. And then often I forget about them after the fact, but if I'm involving static or kinetic friction, I really like to make sure I focus on them. But for now, we're on the ground. These two guys will be the same. There's only one horizontal force acting if you hit your brakes and the tires stop rolling and you start skidding across the ground, and that is your friction. So there's an unbalanced force. So that is all we have to worry about for now. And if we're moving forward, I tend to make forward going to the right. So to start off with the Y direction, I only typically do this once, and then after this, I usually skip this step for most friction problems. First of all, I just want to recognize that a truck is not going to suddenly fly up into the air or crash into the ground. So typically the vertical is in a static state. So that means the two forces that are acting on the truck, so the weight, the truck's weight, and the normal force, if you consider the actual direction, the weight is going down, so therefore your force of gravity is negative. If you bring that over to the right-hand side, so if you bring this over there by addition, your normal is equal to your weight. And so that means your normal force is equal to your mass times your acceleration of gravity. So quite often I skip all of this because, when you do enough of these problems, you just kind of know, oh, there's one force going up and there's one force going down. Okay, well then your normal has to be equal to your weight. If there's two forces going up, obviously I recommend you redo this whole process and try to determine what the normal force is. Or likewise, if there's two forces going down, I would do this process here and try to figure out what the normal force actually is. But if there's just one going up and one going down, you can usually skip all those steps and just go straight to your normal force is equal to your mass times your acceleration of gravity. So if I actually plug the numbers in, you got your 2,300 kilogram truck multiplied by 9.81 meters per second square, and your truck is approximately 2.26 times 10 to the 4 newtons. So approximately 23,000 newtons if we round up. So most of the time, I don't even bother calculating the normal force. I just leave it as mg, and you'll probably see why in a moment. So if we move to the x direction, that is unbalanced. So therefore, we're going to accelerate a little bit. We're going to say to the right is positive because that's just what I'm assuming the positive direction is going. And I'm going to assume that's the way the truck is going. So Newton's second law says my net force equals the sum of all forces, which is equal to your mass times your acceleration. Only one force is acting, so that is my friction force. I know friction should be acting in the negative direction, right? If I define positives to the right, I can see my friction is going left according to my free body diagram. So I'll dump the vector symbol and just go and call it a negative. Knowing that friction has its own equation, I will substitute in that equation for my friction. So this is my kinetic friction. So my kinetic friction is, of course, the coefficient multiplied by my normal. And you can see that I'm going to just steal my normal force from this equation right here. At this point, a lot of people would probably just plug in the numbers because I know students prefer working with numbers, and that's fine. You can definitely just plug in the number instead, but you'll probably agree real quick why I like doing it my way. So if I actually plug in my equation for the weight, mass times your acceleration of gravity, you can see right now that you have mass on both sides, right? And so if you have the same variable on both sides, you can just cancel it out. And my equation gets a little bit easier. So again, if you'd rather plug that in, I won't stop you. Because you can always plug in your normal force, you can plug in your mass, and then of course you can plug in your coefficient, and then you can just work it all out with the numbers as is, but that requires too much calculating for me. So I'd rather just leave it as mass times acceleration of gravity, and then just cancel the masses out. So now that all I have for an equation is nice and quick. I don't have to manipulate the equation. If I plugged in all the other numbers in this step here, I just have to multiply two numbers together. Cuts down on the time it takes to do the problem. So you take your coefficient of kinetic friction, which is 0.8. So it's right there. It is negative because, well, the 0.8 isn't negative. That's just a positive value because there's no direction as far as your coefficient is concerned. But we know friction is negative, so therefore we have a negative as part of our equation. So 80% of the acceleration of gravity is effectively about 7.8 meters per second square. So you're going to slow down at about 7.8 meters per second square. Now I'm not done this problem. I still have a part B, so I'm going to use the 7.848 meters per second square. But as far as following the rules of significant figures, this should only have 2 digits by the time we're done. So moving forward, what distance does the truck need to come to a stop? Knowing what my acceleration is that I just finished calculating, I'm going to take the whole number because why not? I'm still moving forward. Recognize that the truck was initially going 14 meters per second. It's coming to a stop. So therefore the number's not in the question, but you need to just know that if it comes to a stop, the value is 0. and we're looking for how far it actually moves forward. So given my acceleration, my initial velocity, and my displacement, I would probably use this kinematic equation. Final velocity square is equal to your initial velocity square plus 2 times your acceleration times your displacement. If you do a quick equation manipulation, just bring your initial velocity over the other side by subtraction, and then divide both sides by 2 times your acceleration. You'll end up with this manipulation. Plug in the numbers. All right, 0 minus 14 meters per second squared is negative 196 meters squared per second squared, then divided by a number that's just a little under 16. And you'll probably end up with something like 12.6 meters. And if I follow the rules of significant figures and significant digits, I should only have 13 meters as my final answer. So moving forward, 13 meters. If you remember how big the classroom is, that's just a little bit longer than the length of our classroom. Because I believe wall to wall is just shy of 12 meters. So it would be just a little bit longer than our classroom. So that's a pretty long ways to stop. Going at just regular city speed limits. So consider that when you're driving. I'll do a second question now, and I'll try to do this a little bit quicker. A little bit different scenario. Suppose you're pulling a crate across the floor with a rope. The tension in your rope is 400 newtons, and the mass of the crate is 150 kilograms. If the coefficient of static friction is 0.25 and the coefficient of kinetic friction is 0.2, will the crate move? So you'll get that every once in a while. How much force do you need to make something move in some of your example problems, maybe even on some of your quizzes or exams. So just, you probably can set it up just like this question. So always start with a free body diagram whenever you're involving forces. Again, I start with vertical forces. So again, there's no other vertical forces other than the weight and the normal force. So that just gets drawn in nice and quick. We or you or whoever is pulling something. And therefore, again, I try to draw all my positive motions in the x direction to the right. So my applied force, or my tension, if I'd rather call it tension, is being pulled to the right. We know there's friction. It specifically says that, but this is a friction video. So yes, there's friction. It's going in the opposite direction of motion as my tension. So I got that all drawn in. That's all there is for forces. So motion will only begin if my applied force, or all the forces that are pulling to the right, in this case, just the one applied force, is greater than or equal to my force of static friction. So let's just figure out what my force of static friction is just by, oops, I put a K there when I should have put an S. So I'll take my coefficient of static friction, right, the 0.25, and that's equal to my normal, sorry, let me say that again. So my force of static friction is equal to my coefficient of static friction multiplied by the normal force. My normal force, since there's only two forces, should be the same as my actual weight. So skipping all those steps from the previous question, I would just come to the same conclusion that my normal is equal to mass times acceleration of gravity. If you want to see where this came from, just go back a minute or 5 to where I got to that. So I'll just skip to that. Again, don't know what happened there. Bad type job. So I'll just plug in my actual values for that. Again, I'm going to use my coefficient of static friction because this thing was not moving to begin with. Plug in my 0.25 multiplied by the mass of the actual crate, multiplied by 9.81 to get the actual weight. And then you should find that you have a coefficient of static friction to be, the force of static friction to be about 370 newtons. So 370 newtons is definitely greater than my, less than my applied force. So my applied force is greater than my force of static friction, which means motion is going to occur. You are going to be able to pull this crate across. If your tension was less than that, maybe you only had maybe you're only pulling with 350 newtons, the crate wouldn't budge. So now I know this is not part of the question, but we're going to move on to part B. So since we can get it to move and we know we have a kinetic friction, Sometimes both are given just to see if you know which one to put in the actual equation. But often there would be a part B where you would go one step further and say, okay, well, now that the crate is moving, what is the actual acceleration? So that's what we're going to do next. What is the actual acceleration if the crate is actually moving? So in the positive direction, in the x direction to the right, we've got my applied force. So Newton's second law says my net force in the x direction is equal to the sum of all forces in the x direction, which is equal to mass times the acceleration in the x direction. I only have two forces in the x direction. I have my applied force and my force of friction. In this case, it's my kinetic friction. So knowing that my kinetic friction is going to the left, I'll dump both vector symbols. So my applied is going to the right, so that's positive. So I'm going to dump my vector notation as I go from this step here to the next step down there. So this guy remains as a positive. This guy is going backwards, so I call it negative. And therefore, since I know what my coefficient, oh, I'm doing terrible with typing today. I know what my coefficient of kinetic friction is 0.2. I'm going to want to multiply it by the normal force. And very often I would just skip these steps here and just go straight to this last step here. Apparently I'm not consistent with typing. There we go. So my applied force is subtracting by my equation for my kinetic friction. All right, so again, often I just skip those and I just delete them in this video, which is great because there was a typo in there that bothered me. So my applied force subtract my friction, I just got to calculate it still, should be equal to my mass times acceleration. So plugging in all the numbers, you've got 400 newtons minus my coefficient of kinetic friction, which is 0.2, multiplied by the mass of the object, multiplied by the acceleration of gravity, should be equal to the mass of the object times this unknown acceleration that we're trying to find. So in the end, I've got 400 newtons minus 294, so almost 300 newtons. So a little bit different than the 370. So if you remember from a couple minutes ago, the force of static friction was approximately 370 newtons, so quite a bit more. So about 76 more newtons more than the actual kinetic friction. So typically, your static friction will always be bigger than your kinetic friction. I'm sure there's an example where it wouldn't be, but let's not split hairs. So do a little bit of math. So 400 minus 294 is 106 approximately, because again, this was not a perfect 294. I just rounded the number up a little bit. Divide both sides by your actual mass, 150, and you should get an approximate acceleration to two significant figures of 0.70 meters per second square. Right? So that's just how you would do a problem like that. And you'll have a couple problems that are similar to this at some point in the near future, I'm sure. So hopefully that was helpful for you. Review it again if you have to. There's slightly different online notes. I think your questions start on page 39 if my page numbers are correct. And I think there's about, ooh, typo. Man, I'm good with typos today. Where's number 2? Oh, it doesn't matter. Apparently I skipped number 2. I'll go from 1A to 1B to no number 2. Such is life. I believe there is possibly 5 to 6 questions that are in 1-dimension friction, and I'll make a video for 2-dimension friction. In other words, what happens when you're on an inclined plane. So if you have any questions, just fire me an email and I'll get back to you as soon as I can.